All right. So if you remember last time we were talking about RNNs, which yeah, as an opening question to try to refresh our memories a little bit, I'd like you to turn to the person next to you and see if you can explain what is an RNN and when do we use them.
So have your input and that's what is feed it into the network, and then you take your next bit of input and what you got out.
Main thing I have is that you have sort of a bank or a vector that sort of feeds into itself, kind of like a shift of register, like hardware.
Yeah. I don't.
Which makes for interesting policy in the context. It's very, I kind of feels like that just
I agree. I mean, because you use the same network each time, but just some of that, the end result of that network becomes part of it. Which I don't quite understand how that works. Because like, if we start off with letter A, now we have the word A. How do I change that?
a lot of
Or is that how really?
I guess it's hard to visualize that.
I just don't understand what part of recurring was, because
I treat it like you have the same but your network somewhere.
okay.
So you're not really chaining your input. You're just, of course, allowing ways
Okay, so yeah, what did you discuss with your neighbor about what is an RNN and when do we use them? I know. Probably rather hear from the specialist than hear from my droning voice. Yeah, what do you got, Josh?
So it's like a deep learning structure that allows you to produce multiple input or variable inputs and variable outputs instead of just the one-to-one relationship. And how it does that is it takes the new input as well as all the ways from the previous input and runs it through this model over and over as many times as it needs to.
Yeah, great. That's a great explanation, Josh. Yeah, so to review that, RNNs work for tasks where you have a variable length input or output. And there are several different settings. We can do many to one, one to many, many to many, etc. He also talked about how that works, and he talked about how he said we feed the weights from the previous layer in. I just want to make a distinction there. We feed the activations in from the previous layer of the RNN, and then, as you said as well, we also feed in the inputs for the next step. But yeah, that's great. Yeah, and actually, I think a good thing to review before we go any further would just be to talk about the difference between using an RNN, between training an RNN and how you use a trained RNN, because it's a little bit different. In fact, let's see. Do a whiteboard here. Okay, so we got a whiteboard. Okay, so we have an RNN. And let's say we're doing translation. Okay, so we're going to take as input the letter we're going to do the hello example again. The letter H goes in, as well as a hidden state, which we'll call H0. And does anyone remember what H0 is for the first layer of an RNN? Yeah, so you can input a random vector, or you can pass in a 0 vector. Okay, good. So then we will then output another hidden state, H1. And if we are trying to predict the word hello, what would be our training target for HT?
Letter E.
The letter E, exactly. And so we will call this Y1 will be the prediction for that letter E, and we'll just put the letter E over here as a target. So then our network produces a prediction Y1 as well as a new hidden state H1. And that gets passed into the same recurrent neural network with the same weights. So then this second block receives as input the letter E. And what do we want it to produce as its target? The letter L, exactly. And we will call the prediction for that letter Y2. And so at training time, however, we know, like you all have been pointing out, we know exactly what the network is supposed to predict for each of the next letters. And so what we can do is we can actually batch if we're doing this predict the next letter task, we can put our word or our sentence into a batch where H is the first item, E is the second item, etc. And then for our labels, we can also make a batch. But in this case, the batch would start the letter E, L, L, O, and token. Does that make sense? So our input and our output vector is just our input vector shifted by 1. Does that kind of make sense how you would do that to predict the next label? So in this case, you can have a variable length batch size where the batch size depends on the length of the prediction task. However, that's probably a bad idea just because of memory requirements, because then you don't really have any guarantees of how much memory you'll take up. So in practice, probably what you'd like to do instead is crop that sentence to a certain length. And that way you're guaranteed not to have an input that exceeds a certain length. Does that make sense? And so you could crop, and then you could also have some sort of sliding window where you maybe start in the middle of the sentence and go to the middle plus whatever your window size is. So that's training time. So your labels are shifted by 1. At test time, however, we don't know what the labels are. All we have is this trained recurrent neural network, and then we'll have some prompt. So if we want to have a prompt with basically no information, we might prompt it with a start token. So let's draw what that would look like. Also, do you know what I mean when I say training and inference? Or training task? When I say inference is the same thing as task. So training is training a neural network with gradient descent or whatever optimization algorithm. Inference is when you're using a training network to predict on new data. Okay, so this is going to be our same RNN, but used for inference. So we will prompt it with a start token. And then we'll pass in a hidden state. And then what will be the size of what our network predicts for Y1? Any thoughts? You said the size of the source alphabet? What was that? Exactly. Yeah, that is exactly right. So yeah, Y1 will be a vector that has the size of the alphabet of tokens that you have to choose from. So it will probably include all of the lowercase and capital letters. It might also include numbers. It might also include the special start and end tokens that I told you about. And so yeah, let's just say that Y1 is a vector of length 50, and where each entry in that vector represents a probability that the corresponding token will occur next in sequence. Does that make sense to everyone what we're predicting for Y1? Yeah. Yeah, it's a vector of all the tokens that it could be with the probabilities associated with each of those possibilities. Yeah.
So I guess going back to the training, we're still adjusting some weight then, right? Where does that weight fit?
Good question. So for now, that's a great question. So for now, we've been dealing with these RNNs as kind of black boxes, right? Where we don't really know what's going inside. We just know it's some parameterized model that's making a prediction for each of these things. I promise that there are weights inside there, and today we're gonna talk about some of the particulars of how you can hook up the wires. Yeah, good question. Dane?
So essentially the Y vector is like a one-hot encoding for the alphabet we're having in context.
So you use the term one-hot encoding. A one-hot encoding is a little bit different. A one-hot encoding is a vector with the zeros in all slots except the true slot. The difference, so for training, our target E would be, you could think of it as a one-hot vector, because we know with certainty that there is zero probability that the letter E is anything other than the letter E, and then there would be a 1 in the slot for the letter E. However, during both training and inference, Y1, our prediction for that letter, is going to have numbers that are not 0 and not 1, because we have some sort of amount of uncertainty about what will be there. So we wouldn't call it a one-hot vector. We would just call it a vector. Does that make sense? Okay, so we have this vector of predictions, Y1, and we want to predict the next token. So what's one option that you can think of that we might use as our next token for using this RNN at inference time? How can we use Y1 to give us a new input? What was that? Sorry, a little louder. Pick the token with max probability. Great. Yeah, so that is totally an option. So one option is you choose the max. And actually, I guess it would be the argmax, because we're not inputting the probability, we're inputting the token corresponding to the maximum probability. So say argmax over Y1. Yeah, so that is totally an option. So the first letter might be the letter H or the letter A or something like that. Yeah. How is this useful? Good question. So we'll look at some more applications later. So one of the things that you can do is, well, you can imagine, you can set up a problem where your job is to, the RNN's job is to start with a list of facts and then write a news story in prose based on those facts. Or your job could be to take as input a news story and summarize it in 2 sentences, or a Wikipedia article and summarize it in two sentences. So those are not exactly this next token prediction problem. I mean, one application of the next token prediction problem is next token prediction is like the AI dungeon example that we showed you early in the class. And we'll show some more applications that hopefully can inspire you with some more creative ways you can use these RNNs. Yeah. Yeah, great question. So the question is about where we're getting the hidden layer. Are you wondering about H0 or about H1 and the subsequent hidden layers? You're wondering about the subsequent hidden layers. So you can think of H1 as a memory vector. Its job, or a summary vector. Its job is to carry information from all of the previous tokens in the sequence as input to the RNN. Because you can imagine, like, if the RNN was only able to look at the current token to predict the next token, that would make it a lot less powerful than being able to look at the entire sequence of preceding tokens to predict the next token. In fact, probably the best you could do is just predict, is just have the same distribution every time for a given input token, because it wouldn't change at all based on the context. Yeah, okay, so going back to how we can use this at inference, we can take the argmax over y1 and use that as input to the next unit of the recurrent neural network. Any other ideas of possibilities, or maybe places where we could fail if we only ever take the maximum probability token? Yeah, what do you think?
Well, in one of the readings, like they like for super, there's this like temperature thing, like so it would basically generate a loop of things that a loop of words just because it would keep on choosing the most.
Exactly. Yes. What you just pointed out is exactly the failure mode that you see when you take the maximum probability every time. What you pointed out was that if we're going to take the maximum probability, then there's a pretty good chance that there are some sequences of words that occur with high probability. And it turns out that if, for example, for those of you who are familiar with the Book of Mormon, if you train an RNN on the Book of Mormon and you pick the argmax every time, it spits out, and it came to pass, 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 and it came to pass. As you know, you probably know that's a phrase that comes up quite often in the Book of Mormon. And so, yeah, there's some potential issues there from choosing the argmax. Now, you mentioned another word that's very important called temperature. So temperature is a term that's used to refer to the amount of randomness that we include in our predictions. So another option for what we provide as input is what we would call sampling. So how that works is we sample from the vector y1 of probabilities according to the probabilities in that vector. So what that looks like is, so if y1 had length 2 and each of those probabilities was 0.5, then half of the time we would sample position 0, and half of the time we would sample the token at position 1. If the probabilities were 0.75 and 0.25, then 75% of the time we would sample token 0, and 25% of the time we would sample token 1. So that's what sampling is. And then you can also include with a sampling algorithm, you can also include temperature. What temperature does is it basically squishes probabilities. So for high temperatures, it brings probabilities closer to uniform probability. So in our case of if y is length 2, instead of 0.75 and 0.25, it would make them like 0.66 and 0.33. So that would be increasing the temperature of your sampling from that probability vector. And if you had like maximum temperature, then you would just be sampling each of the probabilities with equal probability. If we had, what do you think would happen if we turned the temperature down to 0? So turning the temperature up means that we're sampling uniformly. If we turn the temperature down and our original probability vector is 0.75 and 0.25, what do you think might happen? Yeah, Brendan. You only sample the most probable. So yeah, temperature 0 is actually equal to argmax. Does that make sense? Okay, so yeah, another option is sampling. I won't go very much farther into detail on this, but there are other options that are variations on both of these. There's one called beam search. Beam search basically is like argmax, but instead of taking the maximum value here, it takes, so for a beam search of size 4, if we have 4 beams, it would take the 4 most probable predictions and pass them all into here, and then it would get new predictions, and then it would take the top the top 4 predictions. So now if we have, let's say there are 50 classes, and then we've chosen 4, we get 50 times 4 probabilities for the next token. We then take the top 4 out of those 200 probabilities as our next step. So basically, Y1 or our first letter is never finalized until we look at the probabilities a couple of tokens down the road. And basically, what that allows you to do is instead of just predicting a token that will be highly probable next, it allows you to kind of look down the road and see, well, if none of the subsequent tokens after that token have low probability, we're going to go with another token that may be lower in probability next, but has other subsequent tokens that are higher in probability. I'm sorry, that was not the best explanation, but basically the takeaway is you can, beam search allows you to look further down the road in decoding probabilities. And there are variations of sampling with beam search, as well as doing a greedy argmax technique with beam search. And so if you're wondering about like all the different ways that you could think of to select this next token, these are called decoding algorithms. So if you look at like RNN decoding algorithms, you can get more ideas about how you can select the next token for your RNN. Yeah, question. Yeah, so what was that? No, so we would still start with the start token. So yeah, you can only start with one beam, but like then that expands to 4, and then you maintain four beams throughout the rest of the decoding process. And then you pass each of those separately into the next layer of the network. So you get 50 probabilities for each of those 4 beams that we're decoding. Correct. Yeah. All right. So hopefully that's helpful for some intuition when you're thinking about, training versus inference in recurrent neural networks. And also like that's something you should pay attention to in general, because usually papers talk about how a network is trained and not as specifically about how it's used for inference. And so often they're quite different. And so just be aware of that and know that it's not always like the most straightforward thing, the difference between training and inference for different architectures. I see a hand somewhere over here. Okay. We'll stop that whiteboard. Go back to our PowerPoint. Okay, so here is an example of predictions from an RNN trained on URLs. So at the top, on the top row of each of these, we have a URL. And on the subsequent rows, we have the top token probabilities. So yeah, each of these is probabilities for the next token. So what do you notice here about which characters the network is having an easy time predicting versus a hard time? And oh yeah, and larger numbers are in darker red. Smaller probabilities are in white. Yeah, so the top row is the ground truth. The subsequent rows are the probabilities of the of the top 5 most probable tokens, with the most probable next token in the top row, and the least and the 5th most probable token in the bottom row. And then that's just repeated in each of these blocks. So the question is, what are you noticing about which tokens are easy to predict and which are hard to predict? Yeah, Joseph. Yeah, so you're pointing out that if we're looking at words, they're pretty easy to predict. So I'm seeing news, N predicts E as the next letter, which N is. E predicts T as the next letter, which it's not, but its second highest prediction is W, which is the next letter. After we have new, S is definitely the most probable. And yeah, so it does pretty well at that. It also does pretty well at autocompleting.com. You kind of see that. And then, yeah, what do you notice about the distribution over letters following the dot? Yeah, anything? Yeah. Yeah, exactly. Yeah. So we .c is the most probable, but then we also have .o for .org, .e for .edu, .g for .gov, .n for .net. So it seems like that you can kind of see that the network is really learning to pick up on some patterns here. Okay, that's pretty much what we wanted to get out of that slide. Yeah, that's just another example of translation. Okay, so we talked about how this H vector, we're going to initialize it to be 0 or randomly initialize it. Well, here's a case where we want to condition our recurrent neural network on something. And that hidden state vector provides a nice place to put that conditioning information. So what we're going to do is we want to do image capture. And so what we're going to do is we're going to take this image, pass it through a CNN, and obtain a feature vector representing that image, which will then become our H0, the first hidden state passed into our recurrent neural network. And then from there, we just do normal next word. In this case, our RNN is word level instead of character level. We're just going to try to predict the next word in the sequence. Does that make sense? Yeah. Good question. So yeah, the question is about tokenization. At what level is it normal to break our inputs up? Do people use words? Do people use letters? I believe the most common that people use these days is actually called word piece, where it's like subwords. And so, yeah, there's a trade-off there. You can imagine that if we use words, we're going to have a much larger vocabulary than if we just use characters. And so if we have more data, that might be a good thing. But if we have low data, it's probably if we're getting into some rarer words, then it's probably going to have a hard time. So I would say that if you have a large training set, you can probably increase your token level. If you have a smaller data set, you probably want to go down to like word pieces or characters. Make sense? Okay. And the way that they determine which word pieces to use are word fragments is they basically just scan over data sets and find the most common pairs or trios or quartets of numbers. If you're familiar with Huffman encoding, something along those lines. Yeah, so the word pieces include some common words and then also fragments of less common words. Okay, so yeah, we have a convolutional neural network and a recurrent neural network. So before we go to the next slide, think about how you might extract a feature vector from a CNN. How might you use a CNN to turn an image into a vector? Any thoughts? Yeah, what do you think? Yeah, that'd be one option. So after one convolutional layer, take the activation map and just flatten that into a vector. That would be an option. Yeah. Any other thoughts? Yeah, Dave.
If you max pool your different feature channels, that might tell you something. Like in case of the hat, maybe there's a certain number of corners, edges that's associated.
Yeah. So similar idea, but instead of flashing a vector where we still have some spatial information, Dane is just suggesting max pooling over the spatial dimensions so that we just basically have a summary of each different feature. I like that. Yeah, so another option is you can actually take the class probabilities of, suppose we had a classifier that goes to 100 classes. You can think of the prediction of the 1,000 different classes as kind of a feature representation of your image. So what they're going to do is they are going to strip off the classification layer of the network and just take out the 4096 dimensional embedding at the end of the convolutional network. And if you remember the BGG network, this has a 1x1 spatial dimension and then 4096 channel dimensions. Good with that? Okay, so yeah, we simply add that to our first in state. And then we can also transform that with a weight matrix, which we will call WIH. And then again, we can think, so he's using sample. So if he's talking about sampling, are we talking about training or inference? Do we sample during training or inference? Inference, yeah. Sample is a decoding option for inference. And so, yeah, it's describing inference right now. And then once we sample the end token, the caption of our image is complete. So here's an example. This is I believe this is not predictions, but this is labeled data. So this is an example of an image from the MS COCO data set with 120,000 images, and then about 5 one-sentence descriptions, captions of those images. So a man riding a bike on a dirt path through a forest, a bicyclist raises his fist as he rides on a desert dirt trail, etc. So that's what the data set looks like. And then this is the result of a network training on that data set. So you have a man in black shirt is playing guitar. That's pretty good. Construction worker in orange safety vest is working on the road. Also seems pretty good. Two young girls are playing with a Lego toy. I think one of those girls looks young. I'm not sure about the other one. Boy is doing backflip on wakeboard. Yeah, what? Yeah, so you can see why I got tricked out. Why do you think so? Yeah, exactly. So the background is water, but where he's on a trampoline, not a wakeboard. So, and this kind of gets at a common failure mode of CNN is often they end up looking at the background more than they look at the thing that you actually want them to identify. So if you're looking for a horse, the network is going to learn to look for fields and pastures because apparently that's an easier thing than looking for horses. So it's just kind of a good thing to keep in mind that we might have certain ways that we set up networks that we want the network to learn, but it may find different ways of minimizing the loss. You can think of like the loss function as a lossy approximation of what we're actually intending, right? Yeah, a young boy holding a baseball bat. Cat sitting on a couch with a remote control. So you can see it does all right, but definitely not perfect. Okay, yeah, any questions on this captioning task? All right. So last class, someone asked a question about what are some of the failure modes of RNNs? And one of them I mentioned is memory. Another one is vanishing gradients. So if you remember from our lectures on initialization, the deeper a network got, the more the gradients tended to disappear. Now, if we have a network that can carry inputs of variable length, that means our network can theoretically be arbitrarily deep. And so you can imagine that if we have a sequence of length 10,000, then it could be very easy for our gradient of the loss with respect to the first token to get lost in that process. And this is just a mathematical representation of this. If we break down the loss with the chain rule, we end up with this product of partial derivatives going all the way from the end of the network to the beginning of the network. And if all of these, and so that product of partial derivatives can, it's very easy to lose signal there. So that is a primer for the next lecture, which we are about to begin, which is on LSTMs. Okay, so there was a question earlier about what is inside the black box. Well, we're going to tell you. And hopefully it's not too much of a surprise if you've done your reading for the week. Talk about vanishing gradients, LSTMs. So LSTM stands for long short-term memory. And it's one possible choice for what you might include inside your recurrent layer. So the big ideas behind this are you have this identity path going all the way through from the beginning to the end of your sequence. And what we're going to do is we're going to, at each step, at each new token, we are going to remove information and then add certain information to that identity path. So this is the architecture. It looks pretty bad, huh? All right, so let's see if we can break this down. So there are some things in this diagram that you should probably recognize. If we were to blank out everything inside this rectangle, what do you recognize and what looks new? Well, so first of all, we're blanking out everything inside this rectangle for now. I'm just treating this as a black box. What is the same from what you've seen before, and what is different in terms of RNNs? Yeah, so we have an input xt. What else? We have hidden states coming in. Okay. What up? And then also hidden states coming out. Right. What else? Yeah, Josh. Yeah, we have this extra input ct minus 1, and then an extra output ct. So that's the part that's a little bit different about LSTMs compared to vanilla RNNs. All right, so, and then, yeah, this extra C vector is going to be basically our memory storage. That's where we're going to remember certain things and forget other things. Okay, so let's figure out what happens first. I will tell you that this first unit over here is, we're going to call it a forget gate. And it's going to tell us what to forget from CT minus 1. Also, I think there's a rendering error here. This should be a multiply sign. This blue node at the top, and actually all of the blue circles inside the rectangle should be multiply signs. And they represent point-wise multiplication. Okay, so looking at this first block, what do we take as input? Xt, ht minus 1, and ct minus 1. And we are going to, this plus represents element-wise summation or concatenation. And we mentioned the other day that concatenation and summation are very similar operations. So we'll just say, we'll do one of the two. And then this sigmoid represents a weight matrix, or like a linear layer followed by a sigmoid activation. And then, so basically what happens in this forget unit is we will take all of the previous hidden states and memory and the new input as input. Then we will predict a vector and take the sigmoid of that vector and point-wise multiply that new sigmoid vector with the history, with the memory vector. And does anyone have an idea of why that might correspond to forgetting? Yeah, what do you think? Exactly, yeah. So you're exactly right. So you said if we have the right transformation of the input, the sigmoid could set things that the sigmoid could set certain things to 0 and other things to 1. And what happens with them when we multiply that the output of that with the C vector? Well, certain things will be multiplied by 0, which we can think of as forgetting, and certain things will be multiplied by 1, which we can think of as remember. Okay, does that make sense how we get this forget operation? Yeah, question.
You said that somewhere in there are weights that we learn. Is that
Correct.
what all the arrows are?
Good question. So yeah, the arrows in this case do not represent weight matrices. The weight matrix happens inside this sigmoid node. So this is a weight layer. This sigmoid node is a weight layer followed by a sigmoid activation. And these arrows just indicate that we're taking information from the new input and the previous hidden states to make that decision. All right. Let's move on to the next one. This is this one right here. We will call the remember gate. And it consists of this second sigmoid and this new CANH. Okay, so I will tell you, think of this CANH as just a nonlinearity. You're thinking of the sigmoid as kind of a remember forget thing. Don't worry too much about the choice of activation function here. We could probably put like a ReLU in instead of the CANH, and it would be fine. So we have basically the same thing as before. We're going to create a sigmoid vector, but this time that sigmoid vector is acting on a transformation of the input. You see, the sigmoid takes as input CT minus 1, HT minus 1, and XT, but this CANH only takes as input HT minus 1 and XT. Okay, and we can think of this basically as just a linear transformation of that with maybe some sort of feature extraction, and that feature extraction of our input is the output of this CANH function. So then what happens when we multiply that sigmoid vector with this transformation of our input? Yeah. Exactly. That's what we're looking for. So this first sigmoid told us what to forget of our history, and this new sigmoid tells us what we want to remember of our new input. And so when we multiply that sigmoid by this transformation of our input, we're going to have basically some elements of our input set to 0 and others, other elements are multiplied by 1 and remain the same, and then are added on to our history vector. Does that make sense? All right, and so we know how LSTMs remember and forget, and that is where we will end for today.